Tonight, we're going to talk about a discovery that made astronomers genuinely uneasy. For decades, scientists worked out a timeline for how the universe came together, starting from a hot, smooth beginning and arriving at the sprawling galaxies we see today. That timeline predicted something very specific about the early universe. It said the first galaxies should be small, faint, barely formed. Then, the James Webb Space Telescope opened its mirror, turned it toward the deepest darkness ever photographed, and looked back at the beginning of time. And what it found didn't match the prediction. Galaxies showed up too massive, too early, too organized, far more structured than they had any right to be at that point in cosmic history. Supermassive black holes had no reasonable amount of time to grow that large. And an entirely new class of object, unlike anything catalogued before, started turning up again and again across the deepest images ever taken. By the end of tonight, you're going to understand exactly what these discoveries are, why they've forced scientists to question assumptions that had gone unchallenged for decades, and what the leading explanations actually say about how the early universe really came together. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why the James Webb discoveries landed the way they did, you need to understand what the model said before any of this started. The model wasn't a rough sketch. It was a precise, numerical prediction, one that had been tested against observation for decades and kept passing. The standard account of cosmic history begins approximately 13.8 billion years ago. Everything that would ever exist, every gram of matter, every joule of energy, every particle that would eventually form a star or a planet or a living cell, was compressed into a state of incomprehensible heat and density. The mathematics describing that initial state pushes towards singularity, a point where density becomes infinite and temperature becomes infinite, and the equations of physics, as we understand them, break down. We do not know what happened at the singularity. We do not have a theory of quantum gravity capable of describing physics at those extremes. What we know is what happened after. In the first tiny fraction of a second, within the first 10 to the negative 32 seconds, an interval so brief that no human unit of time comes close to capturing it, the universe underwent a period called inflation. Space expanded exponentially fast. Regions that were in contact with each other, that had been close enough for physical processes to establish uniformity, were stretched to distances far beyond what light could subsequently cross. This is why the universe looks the same in every direction. Regions of the sky separated by more than the distance light could have traveled since the Big Bang look identical in their properties. The same temperature in the cosmic microwave background, the same density of matter, the same expansion rate. Under normal physics, they could never have communicated to establish that uniformity. Inflation explains it. They were in contact before inflation stretched them apart. Inflation also seeded the universe with quantum fluctuations. On the smallest scales, quantum mechanics means that even a perfectly uniform field has fluctuations, random variations, in density and energy at the quantum level. Inflation took those quantum fluctuations and stretched them to cosmic scales. Tiny regions that were slightly denser than average became cosmological density fluctuations. These fluctuations are what seeded all the structure that followed. Every galaxy, every cluster of galaxies. every filament of the cosmic web, every planet and star. All of it traces back to random quantum fluctuations in the first fraction of a second, amplified by inflation to become the seeds of cosmic structure. After inflation, the universe continued expanding, but more slowly. The temperature was still unimaginably high. Quark-gluon plasma filled everything. Within the first microseconds, quarks bound together into protons and neutrons. Within the first 3 minutes, protons and neutrons combined to form the lightest atomic nuclei, hydrogen, helium, and a small amount of lithium. This process is called Big Bang nucleosynthesis, and it left a precise chemical fingerprint, roughly 75% hydrogen and 25% helium by mass, with a tiny trace of lithium. This prediction is confirmed by measurements of the composition of the oldest, most chemically primitive stars we can find. It is one of the strongest pieces of evidence that the standard cosmological model is correct. But for the 380,000 years after nucleosynthesis, the universe was opaque. Photons of light could not travel freely. The temperature was too high for electrons to bind to nuclei and form neutral atoms. Free electrons scattered photons in all directions, like light scattering in fog. The universe was a glowing, opaque plasma. Beautiful in principle, unknowable in detail. Then, at about 380,000 years, the temperature fell below roughly 4,900 degrees Fahrenheit, or about 2,700 degrees Celsius, the threshold at which electrons could combine with protons to form neutral hydrogen atoms. This happened rapidly. Within a geologically brief window, the free electron density dropped sharply. The photons that had been bouncing around for hundreds of thousands of years suddenly found themselves in a transparent universe. They streamed outward in all directions. Those photons are still traveling today. They fill the entire sky, arriving at Earth from every direction, stretched by 13.8 billion years of cosmic expansion from their original near-visible wavelengths into the microwave band. We call them the cosmic microwave background. They carry an image imprinted in tiny temperature fluctuations of 1 part in 100,000 of the density structure of the universe at 380,000 years old. Those temperature fluctuations are the imprint of inflation's quantum seeds. We have mapped them in extraordinary detail. The Wilkinson microwave anisotropy probe in the early 2000s and the Planck satellite in the 2010s produced maps of the cosmic microwave background with enough precision to measure the convivalence parameters of the standard cosmological model to better than 1% accuracy. We know the age of the universe to about 1%. We know how much ordinary matter it contains. We know how much dark matter it contains. We know the density of dark energy. We know the geometry of the universe, whether it is flat, open, or closed, to exquisite precision. The standard cosmological model is, in this sense, one of the most precisely tested theories in all of science. And then, after recombination, after that moment of transparency, the universe went dark again. The photons of the cosmic microwave background were gone, streaming away in all directions. What remained was dark. Neutral hydrogen and helium, spread through the universe, slowly being pulled together by gravity into the denser regions that the quantum fluctuations had seeded. No light sources, no stars yet. Just dark gas clouds pulling inward. This period is called the Cosmic Dark Ages. It lasted perhaps 100 to 200 million years. And then, somewhere in those vast dark clouds of primordial hydrogen, gravity finally won. Gas, compressed enough to heat enough, nuclear fusion ignited. The first stars turned on. Those first stars were nothing like the sun. The universe at that point had no heavy elements at all. The only atoms that existed were the ones made in the first 3 minutes: hydrogen, helium, lithium. No carbon, no oxygen, no iron, no silicon, no nitrogen. All the heavy elements we know, all the atoms that make up planets and chemistry and biology, had to be created inside stars and then scattered through supernova explosions. And without heavy elements to help cool the collapsing gas clouds, those first star-forming regions stayed hotter than modern star-forming regions and grew much larger masses. Theorists calculate that the first generation of stars, astronomers call them population 3 stars, were typically hundreds of times more massive than the Sun. Some may have been thousands of solar masses. They burned at temperatures so extreme they produced intense ultraviolet radiation. They lived only a few million years before their fuel ran out. When a very massive star exhausts its fuel, it can collapse catastrophically. For the most massive population 3 stars, the core may have imploded directly into a black hole without a conventional supernova. For slightly less massive ones, the supernova explosion scattered heavy elements, carbon, oxygen, silicon, iron, all the elements forged in the star's core, into the surrounding gas. That enriched gas formed the raw material for the second generation of stars, which were still massive by today's standards, but not as extreme, which had heavier elements to work with, which could form in more diverse ways. And over time, over hundreds of millions of years, those second and third generation stars built the first recognizable galaxies. This picture is well supported by theory, and it makes specific predictions about what the early universe should look like. In the first 100 million years, nothing visible, just dark gas. From 200 to 400 million years, the first stars igniting, scattered, isolated, not yet in organized galaxies. From 400 million to 700 million years, the first tiny proto-galaxies forming, small, irregular, low mass, merging with each other slowly. From 700 million to 1 billion years, somewhat larger galaxies, still not like the Milky Way, still assembling. The first thin filaments of the cosmic web becoming apparent. From 1 billion to 3 billion years. Significant galaxy growth through mergers and continued star formation. Real structure becoming visible. Large galaxy clusters beginning to assemble. From 3 billion years onward, the galaxy population maturing into something resembling the universe we live in today. This is what the models predicted. This is what every cosmological simulation produced. And it matched the observations beautifully for the parts of the universe that previous telescopes could reach. Then Webb pointed at the parts they could not reach. And the story changed. The James Webb Space Telescope launched on Christmas Day, 2021. Getting it to launch required one of the most complicated and consequential engineering processes in the history of space exploration. Webb's primary mirror is 21 feet and 4 inches across, too large to fit inside any existing rocket fairing in a fully deployed state. So it had to fold. 18 hexagonal mirror segments, each coated with a microscopically thin layer of gold to maximize infrared reflectivity, hinged together and collapsed to fit inside an Ariane 5 rocket. The 5-layer sunshield, the size of a tennis court, made of a material called kapton, coated with aluminum and silicon, had to be folded origami style into a bundle that fit the same fairing. After launch, Webb performed a 30-day sequence of deployments in space. The solar panels first, then the antenna. Then, day by day, the sunshield layers, unfolding and tensioning. Then the secondary mirror swinging out on its support structure. Then the two side panels of the primary mirror rotating into place. Every one of these steps had to work. There was no crew to fix problems. No repair mission planned. If any of the 344 single-point failures in the deployment sequence had occurred, the telescope might have been unrecoverable. All of them worked. Engineers had spent years designing deployment mechanisms that could survive the vibration of launch and the thermal shock of transitioning from Earth's environment into the cold of space. The mirror segments had been individually aligned to nanometer precision before launch, then locked into their folded configuration, then had to be realigned in space to nanometer precision again after deployment. This was done using actuators on each mirror segment and a process of wavefront sensing and control that took several months after deployment to complete. By the spring of 2022, Webb's mirrors were aligned. Its instruments were calibrated. And on July 12, 2022, NASA released the first full-color science images. The reaction from the public was immediate and visceral. Thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length. The Carina Nebula resolved in detail that dwarfed anything Hubble had achieved. The spectrum of an exoplanet atmosphere showing water vapor and carbon dioxide with extraordinary clarity. Interacting galaxies in a group called Stephan's Quintet, imaged in infrared wavelengths that revealed structure invisible to previous telescopes. The images were beautiful, but for the scientists, the beauty was secondary. What mattered was what the data contained. And when the astronomical community began analyzing the science data in the months that followed, they started finding things that the models had not predicted. The first anomalies emerged from the deep field observations. Webb's initial deep field programs pointed the telescope at blank patches of sky and accumulated light for many hours or days, collecting photons from the faintest possible sources. In these deep fields, galaxies appeared at redshifts far higher than Hubble had been able to probe in detail. Early photometric analyses identified galaxy candidates at redshifts above 10, above 11, above 12, corresponding to when the universe was less than 400 million years old. None of this was entirely surprising. Webb was designed to find such objects. What was surprising was how many there were, and how bright they were, and what their brightness implied about their mass. In astronomy, you can estimate the stellar mass of a galaxy from its brightness at certain wavelengths, particularly in the near-infrared, where the light from older stars dominates over the light from young, hot stars. The brightness of early galaxies in Webb's infrared bands implied stellar masses far larger than the models had predicted for their epoch. In August 2022, a preprint appeared on the Arxiv, the physics and astronomy preprint server, where researchers share results before formal publication by Labbe and colleagues, reporting photometric detections of massive galaxy candidates at very high redshifts. The paper was careful, and the caveats were clearly stated. These were photometric estimates. The redshifts were not spectroscopically confirmed. The mass estimates relied on assumptions about the stellar populations in these galaxies. But even with conservative assumptions, the implied masses were startling. And within months, similar reports were appearing from multiple independent groups. Teams at different institutions, using different analysis pipelines, finding different samples of early galaxy candidates, all arriving at the same conclusion. The early universe had more massive galaxies than the models said it should. Then, in February 2023, the paper by Labbe and colleagues appeared in the journal Nature, formally peer-reviewed. Results checked and rechecked. 6 galaxy candidates, with masses ranging from tens of billions to roughly 100 billion solar masses, all in the first 800 million years of cosmic history. The most extreme implied masses, if correct, exceeded predictions from the standard models by factors approaching 100. The phrase that circulated through the astronomy community was simple and direct. These galaxies should not exist. Not in the sense that they violated fundamental physics, but in the sense that the models which were supposed to correctly predict the population of early massive galaxies predicted almost none at these masses, at these epochs. Finding many of them meant the models were missing something significant. The debate that followed was vigorous and scientifically healthy. Every potential systematic error was investigated. Photometric redshift codes were rerun with different assumptions. The effects of emission line contamination were modeled. Dust attenuation corrections were varied. Stellar population models were tested. Active galactic nucleus contamination was considered. Some of the most extreme early mass estimates were revised downward. A galaxy initially estimated at several hundred billion solar masses might come out at 50 billion after better analysis, still surprisingly large for its epoch. Less apocalyptic for the model. But after all the revisions, after all the systematic checks, a statistically significant excess of massive early galaxies remained. The most definitive evidence came from spectroscopic confirmation. Webb's near-spec spectrograph began targeting the most interesting early galaxy candidates and taking their spectra, pinning down their redshifts with high precision and measuring the physical properties of their stellar populations directly. The results that came through 2023 and 2024 consistently showed, yes, these galaxies are at the high redshifts the photometry suggested. Yes, they are massive. Yes, their existence strains the predictions of the standard model. The JADES survey, the JWST Advanced Deep Extragalactic Survey, a collaboration between the NIR-CAM and NIR-SPEC instrument teams, covering 2 of the most intensely studied patches of sky in the history of astronomy, became the primary vehicle for this spectroscopic confirmation work. By the end of 2024, JADES had assembled spectroscopic samples of galaxies at redshifts above 6, above 8, above 10. Hundreds of confirmed galaxies at epochs the pre-Webb astronomical community had studied almost entirely from photometry and a handful of confirmed objects. The statistics from JADES made the early massive galaxy problem unambiguous. There is no version of the data analysis that makes it go away. The early universe is more productive than the models said. The mass problem in early galaxies is connected to a related problem that is arguably even more challenging to explain: the black holes. Every large galaxy we know of in the modern universe hosts a supermassive black hole at its center. Our own Milky Way's central black hole, Sagittarius A, weighs roughly 4 million solar masses. The nearest large galaxy to the Milky Way, Andromeda, has a central black hole of perhaps 100 million solar masses. The giant elliptical galaxies at the centers of large clusters host black holes in the range of billions to tens of billions of solar masses. These objects are built into the physics of galaxies. The mass of a galaxy's central black hole correlates tightly with the properties of the galaxy's stellar bulge, the distribution of older stars around the galactic center. This correlation suggests that black holes and galaxies co-evolved. Their growth was connected. They influenced each other. Understanding this coevolution is one of the central goals of galaxy formation theory. But before we can understand coevolution, we need to understand origin. Before the question of how black holes and galaxies influenced each other is the question of where the first supermassive black holes came from. And Webb has made this question considerably sharper and more urgent. Before Webb, astronomers had identified a handful of quasars galaxies with actively accreting supermassive black holes blazing with the energy released by infalling matter at redshifts above 6, corresponding to when the universe was less than 1 billion years old. The most distant confirmed quasar before Webb's launch sat at a redshift of about 7.6, corresponding to when the universe was about 700 million years old, and hosted a black hole with a mass of roughly 1.6 billion solar masses. This was already a severe problem for models of black hole formation and growth. 1.6 billion solar masses at 700 million years requires, under any standard accretion model, that the black hole started massive and grew continuously at the maximum possible rate for its entire existence. The maximum accretion rate, the Eddington limit, depends on the black hole's current mass. A black hole accreting at the Eddington limit doubles its mass on a characteristic timescale of about 45 million years. Starting from a stellar remnant black hole of 30 solar masses, doubling every 45 million years, growing for 700 million years, you end up with a mass of about 10 million solar masses. Not 1.6 billion. The numbers don't close. Not even at maximum accretion from a reasonable starting mass. For all available time, Webb made this problem worse. Not by disproving the existing high redshift quasars, but by finding more active black holes at higher redshifts and at lower luminosities, meaning these are not just the rare, spectacular, billion solar mass monsters that can be detected across cosmic distances by their extreme luminosity. These are a broader population of less extreme, but still surprisingly massive, accreting black holes, detectable now because Webb is sensitive enough to find them. The object designated UHZ1 is a striking example. Identified through a combination of Webb imaging and Chandra X-ray Observatory observations, UHZ1 sits at a redshift corresponding to when the universe was approximately 470 million years old, the highest redshift X-ray active black hole ever detected at the time of its discovery. It is actively accreting. Its X-ray luminosity indicates that the accretion rate is close to or exceeding the Eddington limit. Its black hole mass is estimated between 10 million and 100 million solar masses. 10 million to 100 million solar masses at 470 million years. The Eddington doubling argument applied to this system gives the same answer it always does. You cannot grow from a stellar remnant to this mass in this time. Something else happened. The something else has several candidates, and they are not mutually exclusive. The first and most developed is direct collapse. The idea is that in certain regions of the early universe, massive gas clouds bypass the normal star formation process entirely. Normally, gas clouds cool and fragment. Molecular hydrogen radiates heat efficiently, allowing the cloud to shed energy, compress, and break into smaller pieces, each of which forms an individual star. But if molecular hydrogen is suppressed, if intense ultraviolet radiation from nearby sources destroys the molecular hydrogen before it can cool the gas, the cloud stays hot. Without efficient cooling, without fragmentation, the gas collapses as a single coherent mass. It forms a massive central concentration, not a collection of stars, but a single superstar object, which then collapses into a black hole, without ever going through a conventional stellar evolution. This direct collapse black hole starts with a mass of 100,000 to perhaps 1 million solar masses. That is the starting mass. From there, even at moderate accretion rates, reaching 100 million or 1 billion solar masses becomes achievable within the available time. The required conditions, intense ultraviolet radiation to destroy molecular hydrogen, metal-free gas to prevent alternative cooling pathways, were plausibly present in certain environments of the early universe. Regions near the most massive and luminous of the first generation of population 3 stars could have provided exactly the radiation field needed to enable direct collapse in nearby clouds. The direct collapse mechanism has been theorized for many years. What Webb is providing is observational constraints on how often it happened and what the resulting black holes look like. The challenge is that direct collapse events are brief. A cloud collapsing directly into a black hole does so on a dynamical timescale, millions of years, which is brief on cosmological scales. Finding one in the act requires knowing where to look and having the sensitivity to detect a source that may not be particularly bright in any single wavelength. But the accumulated population of direct collapse black holes, the black holes that formed this way and then grew through accretion, should be detectable through their effects on the surrounding galaxy, and through the quasar and active galactic nucleus populations that Webb is now surveying. The second mechanism is one that has gained renewed attention from Webb's discoveries specifically: quasi-stars. In the extreme conditions of the earliest universe, certain massive gas clouds may have formed objects so enormous that they could not be supported by nuclear fusion alone. For a normal star, the energy of nuclear fusion in the core creates outward pressure that balances gravity. The star sits in hydrostatic equilibrium. But for an object of 10,000 to 40,000 solar masses, the amount of fusion energy required to support the star's weight exceeds what nuclear burning can provide. These supermassive protostellar objects would collapse immediately after formation, except that as they collapse, the infalling gas gets hot enough and dense enough to trigger accretion onto the forming black hole at the center. The energy released by accretion can partially support the outer layers of the star. So what you get is an enormous, quasi-stable object, a quasi-star, that is glowing with both nuclear fusion and accretion energy, with a growing black hole embedded at its center. These objects would be extraordinarily luminous. Millions to perhaps tens of millions of times the luminosity of the Sun. They would persist for thousands to millions of years before the growing central black hole consumed enough of the surrounding stellar material to cause the outer layers to collapse or disperse. When they finally ended, the black hole at the center would have already grown to masses far exceeding anything a conventional supernova could produce, potentially millions of solar masses. And from that starting point, conventional Eddington limited accretion can reach the observed early black hole masses comfortably. Webb has not directly confirmed a quasi-star. These objects, if they exist, would be challenging to identify clearly. They would look like an unusually compact, unusually luminous point source in the early universe, bright in the infrared from the accretion energy, with spectral features that might not match either a normal galaxy or a standard active galactic nucleus cleanly. Which brings up something that Webb has found in abundance and that has not been cleanly identified as anything else yet. Beginning in mid-2023, researchers analyzing multiple Webb deep field surveys began flagging a class of objects that didn't fit existing templates. Compact, point-like, or nearly point-like, in Webb's imaging, intensely red in color, surprisingly luminous, and appearing in numbers far exceeding what any pre-Webb model had predicted. The informal name that stuck is little red dots. It is descriptive. In the infrared color images Webb produces, these objects appear as compact, intensely red points. A paper by Matthey and colleagues, published in the Astrophysical Journal in early 2024, presented a sample of several hundred little red dot candidates identified across 3 Webb deep fields. The paper documented that the number density of these objects in the early universe, how many exist per unit volume of cosmic space, is far larger than any model for early quasars or early compact galaxies had predicted, by factors of 10 to 100 or more in some redshift ranges. Their spectra, where obtained, were strange. Many showed broad emission lines, characteristic of gas moving at thousands of miles per second, the kind of velocities only found near accreting supermassive black holes. This would make them active galactic nuclei of some kind. But their other properties didn't fit standard active galactic nucleus models. Their sizes were more compact than typical quasars. Some showed simultaneous signatures of both active accretion and intense ongoing star formation in a very small volume. Some showed absorption features in their spectra that are hard to explain with either pure starburst or pure active galactic nucleus models. Multiple interpretations are actively being pursued. Some fraction of the little red dots are probably compact starburst galaxies, galaxies forming stars so intensely that their emission is dominated by massive young stars, with the red color produced by dust reddening rather than by the intrinsic redness of the source. Some fraction are probably accreting black holes in unusual states, possibly super-Eddington accretion, where the black hole is consuming matter faster than the standard Eddington limit, would suggest possible, producing a different spectral signature than typical quasars. Super-Eddington accretion is theoretically possible in certain conditions and has been proposed as a mechanism for rapid early black hole growth. If early black holes commonly accreted at super-Eddington rates, this would significantly relax the constraints on how quickly they could grow, from modest starting masses to the billions of solar masses we observe. Some fraction of the little red dots may be the observational signatures of quasi-stars or related objects. As of early 2026, the little red dot population remains one of the most actively studied and most contested topics in the early universe literature. Multiple independent research groups are chasing spectroscopic follow-up observations. Detailed modeling of the emission mechanisms is ongoing. The debate about their nature is not yet settled, but their existence is not in doubt. Webb found hundreds of them. They are real. And the early universe apparently produced far more of them than anyone predicted before Webb launched. The black hole and galaxy surprises from Webb arrived alongside a third category of unexpected finding: the scale of structure in the early universe. In the present-day universe, matter is distributed in what cosmologists call the cosmic web. a vast, three-dimensional network of filaments, walls, and nodes, sheets of galaxies, stretching across hundreds of millions of light-years, with massive galaxy clusters sitting at the nodes where filaments intersect, and great empty voids between the filaments. The cosmic web is one of the signature predictions of the cold dark matter model. It arises because dark matter halos form hierarchically. Small halos collapse first. They attract neighboring gas and dark matter. They merge with each other. They grow into larger halos. And those larger halos merge in turn. The result is that matter condenses along lines and sheets determined by the initial density fluctuations from inflation, progressively organizing itself into the filamentary cosmic web structure we observe today. We can map the cosmic web in the nearby universe with extraordinary fidelity. The Sloan Digital Sky Survey and subsequent large galaxy redshift surveys have traced it across volumes spanning billions of light-years. It looks exactly like what the cold dark matter simulations predict. This is a major triumph of the Standard Model, but the model also predicts when this web assembled. Specifically, it predicts that in the first billion years, the universe should have been relatively smooth. The density fluctuations were still small. Gravity had not yet had time to amplify them into strongly organized structures. The first protogalaxies should have been scattered somewhat randomly. Genuine protoclusters, gravitationally bound overdensities containing many massive galaxies. The precursors to the massive galaxy clusters we see today should be rare in the first billion years. Extended filamentary structures connecting multiple early galaxy overdensities should be essentially absent. Webb found them. An observational result that generated significant attention in 2023 involved a confirmed protocluster at a redshift corresponding to when the universe was about 700 million years old. Multiple spectroscopic members confirmed in the same region of sky. An overdensity of galaxies organized in a filamentary pattern extending across tens of millions of light-years. Individual galaxies within the structure, showing spectral signatures of having already experienced multiple generations of star formation, implying the star formation in this region began well before the observed epoch. A 2024 study using near-spec traced galaxy velocities in an overdensity at a redshift of about 7.7 and found that the velocity distribution was consistent with the galaxies, being gravitationally bound, a genuine protocluster in the making. The estimated mass of the dark matter halo hosting this system placed it among the most massive structures that should have existed at that epoch under the Standard Model, should have been essentially unique. Instead, Webb found it in a relatively small survey area, suggesting structures like it are not as rare as predicted. The frequency with which Webb finds these early large-scale structures, overdensities, protoclusters, hints of filamentary organization, is itself a statistical signal. Individual structures can always be explained away as tail-end fluctuations, the rare cases where the density happened to be high by chance. But when you find multiple such structures in a survey of limited sky area, the probability of all of them being rare fluctuations becomes small. The statistics indicate that the early, large-scale structure of the universe is more developed than the Standard Model predicted, more organized, more concentrated into overdense regions at an earlier epoch. This is consistent with the early galaxy mass problem. Both are saying the same thing in different languages. Structure in the early universe assembled faster than the models expected. Then there are the galaxies that should not have been done yet. Quenched Galaxies. In the present-day universe, galaxies fall into two broad populations. There are actively star-forming galaxies, still converting gas into stars, typically spiral in structure, blue in color from the light of their massive young stars. And there are quenched galaxies, which have stopped forming stars, whose stellar populations are old and cooling, which appear red in color, because only the long-lived lower-mass stars remain. The Milky Way sits somewhere in the middle, still forming stars, but at a modest rate compared to its peak activity several billion years ago. Many of our nearby neighbors in the local universe are quenched. The giant elliptical galaxies that dominate massive clusters are typically quenched. Their star formation history shows intense activity billions of years ago, followed by an abrupt cessation, after which they have coasted on their accumulated stellar mass. The process that shuts down star formation in a massive galaxy is called quenching. It requires removing or heating the galaxy's gas supply, the raw material from which new stars would form. The two leading quenching mechanisms are stellar feedback, the winds and supernova explosions from massive stars, injecting energy into the surrounding gas, and active galactic nucleus feedback. The powerful winds and jets launched by an actively accreting supermassive black hole that can heat gas and blow it entirely out of the galaxy. The second mechanism is thought to be dominant in the most massive galaxies. A sufficiently massive and actively accreting central black hole can, in a relatively brief burst of activity, deposit enough energy into the galactic gas to quench star formation permanently. The timeline for this process in the pre-Webb model was clear. Quenching requires a galaxy to first build up substantial stellar mass, implying an extended period of active star formation. It then requires a mechanism, typically active black hole feedback, powerful enough to clear or heat all the available gas. And it takes time for both phases to complete. Pre-Webb models predicted that truly quenched galaxies would be rare before about 2 billion years of cosmic age. Before 1 billion years, they should be essentially absent. Webb found them before 1 billion years. Galaxy candidates whose spectral energy distributions, the pattern of their brightness, across many wavelengths, were consistent with stellar populations that had already stopped forming. Stars, in the first 1 to 2 billion years. Initial photometric identifications were followed up spectroscopically by several groups through 2023 and 2024. The spectroscopic confirmations showed galaxies with stellar ages, implying that the bulk of their star formation had ended hundreds of millions of years before the observed epoch. In the most extreme cases, galaxies observed at a redshift corresponding to 1.5 billion years showed stellar populations whose peak formation was at redshifts corresponding to under 500 million years. A galaxy that formed most of its stars in the first 500 million years had its star formation quenched by some mechanism within that brief window, and was then observed as a red, dead galaxy less than 1 billion years into cosmic history. That requires star formation rates hundreds to thousands of times higher than the Milky Way's current rate, sustained for hundreds of millions of years, then stopped completely by a mechanism powerful enough to remove or heat all available gas from a massive galaxy permanently. That mechanism, operating at those rates, implies a supermassive black hole, massive enough to produce that kind of feedback, accreting actively enough to do it, within the first few 100 million years of cosmic history. Every piece of this picture pushes the required black hole activity earlier. The timeline of early black hole growth, implied by the early quenched galaxy population, is, if anything, more extreme than what the early quasar observations alone require. The early universe was not building its complexity slowly. Something was driving it to sprint. And the question of what exactly that something was is now one of the central open problems in astrophysics. At this point, it is worth being precise about what Webb's discoveries do and do not imply for the standard cosmological model. Because the way this story sometimes gets told in popular accounts shades toward the claim that everything we know about cosmology is wrong. That is not what the data says. Lambda CDM is not broken. It is one of the most precisely tested scientific theories ever formulated. Its predictions for the cosmic microwave background match observations to better than 1% across dozens of independent parameters. Its predictions for the large-scale distribution of galaxies, the baryon acoustic oscillation scale, the expansion history of the universe, the abundance of galaxy clusters, and the properties of the intergalactic medium are all consistent with observations to a level of precision that took decades to achieve. The foundations of lambda CDM, general relativity, quantum field theory, the hot Big Bang, cosmic inflation, cold dark matter, and the cosmological constant are not in question. None of Webb's discoveries require revising any of these foundational elements. What is in question is a second layer of physics that operates within this framework: the astrophysics of star formation, the astrophysics of black hole, seeding and growth, the astrophysics of feedback, how energy from stars and black holes interacts with the surrounding gas, the astrophysics of how dark matter halos assemble and how gas falls into them. These are complicated, messy, non-linear physical processes. They operate on scales from individual stars to entire galaxies. They involve magnetic fields, turbulence, radiation transfer, shock waves, chemistry. Simulating them accurately requires enormous computational resources and many simplifying assumptions. The pre-Webb simulations were the best available at the time. They made reasonable assumptions about these processes. But they were calibrated primarily on observations of the relatively nearby universe. Extrapolating those calibrated assumptions into the regime of the very early universe, where conditions were more extreme, where gas densities were higher, where temperatures were higher, where no heavy elements existed, where everything was happening faster, introduced uncertainties that the pre-Webb data could not expose. Webb exposed them. The early universe had more efficient star formation than the models assumed. It had more rapid black hole growth than the models assumed. It assembled large-scale structure faster than the models assumed. These are not failures of the cosmological model. They are failures of specific astrophysical submodels built into the galaxy formation simulations. And those submodels can be revised, are being revised, will be revised more thoroughly as more Webb data arrives and more spectroscopic samples are assembled. The revised models will be better. They will make more accurate predictions about the early universe. They will be tested against the next round of observations. And if they still disagree with what we see, they will be revised again. This is not unique to cosmology. It is the normal trajectory of a mature scientific field when confronted with significantly better data. The fundamental architecture is sound. The details needed updating. Webb is providing the data needed to update them. Several specific directions for revision are being actively explored. The first involves the stellar initial mass function in the early universe. The initial mass function describes how stars of different masses are distributed when a cloud of gas collapses to form a stellar population. A standard, present-day initial mass function produces far more low-mass stars than high-mass stars. For every star more massive than 10 solar masses, there are hundreds or thousands of stars smaller than the Sun. This distribution is well established in nearby star-forming regions. But theorists have long predicted that the initial mass function in the very early universe, in the metal-free gas of the first population 3 star-forming regions, should be different. Without heavy elements to cool the gas efficiently, the gene's mass, the minimum mass required for a gas cloud to collapse against its own thermal pressure, is much higher. This means the early universe preferentially formed massive stars. The initial mass function was top-heavy. Pre-Webb models typically used an early universe initial mass function that was somewhat top-heavy, but not dramatically so. Webb's early galaxy observations suggest the models underestimated the degree of top-heaviness. A significantly more top-heavy initial mass function in the first billion years would produce more ultraviolet and visible light per unit of stellar mass, making early galaxies appear brighter and more massive than their true stellar mass would imply. This would bring the observed luminosities into better agreement with the models, without requiring the galaxies to have truly extraordinary stellar masses. Several papers, published in 2023 and 2024, have explored top-heavy early initial mass functions and found them to be a promising partial resolution to the early galaxy. Problem: the degree of top-heaviness needed to resolve the discrepancy is large, significantly larger than what was typically assumed in pre-Webb simulations. But it is consistent with theoretical predictions for metal-free star formation. The second direction involves feedback efficiency. Standard galaxy formation models include recipes for stellar feedback, how much energy and momentum are deposited into the surrounding gas by supernovae, stellar winds, and radiation pressure from massive stars. These recipes are calibrated to match the observed properties of present-day galaxies. But in the dense, hot, gas-rich environments of early galaxies, the efficiency of stellar feedback may have been different. Specifically, it may have been lower. In today's galaxies, supernova explosions can efficiently blow gas out of star-forming regions because the gas density is relatively modest. In the much denser environments of the early universe, supernova ejecta may have radiated away its energy more quickly before it could do much work on the surrounding gas. This is called the overcooling problem, and it has been discussed in galaxy formation theory for years. If stellar feedback was less efficient in the early universe, then more gas would have remained available for star formation, and galaxies would have formed stars more rapidly. This would explain the early galaxy mass excess without requiring the initial mass function to change. Or both effects could be operating together. A combination of more top-heavy stellar populations and less efficient feedback could explain the observations, while neither effect alone needs to be as extreme. The third direction involves the dark matter model itself. Standard cold dark matter predicts a specific rate and spatial distribution of dark matter halo formation in the early universe. These predictions translate into specific predictions for how many massive early galaxies should exist at each epoch. Some researchers have explored whether modifications to the dark matter model, making the dark matter slightly warmer, or including self-interactions between dark matter particles, or including mechanisms for dark matter to produce extra density fluctuations on small scales, could shift the halo mass function in the early universe in ways that better match Webb's observations. None of these alternatives has been shown to provide a clearly better fit to all the data than standard cold dark matter. But they are being explored. And Webb's early galaxy data provides new constraints that future modifications will have to satisfy. The question of the cosmic horizon is one that most discussions of Webb's discoveries skip past. But it is perhaps the most philosophically significant aspect of what Webb is doing. The observable universe has a finite boundary, not an edge in the sense of a wall or a surface, but a limit imposed by the combination of the finite speed of light and the finite age of the universe. Light can only reach us from objects that were close enough when they emitted it for the light to outrun the expansion of space and arrive here in the time since the Big Bang. Objects farther away than a certain distance had their light launched on a journey that the expansion of space has been stretching faster than the light could travel. That light will never arrive. The distance to the edge of our observable universe, the cosmic horizon, is about 46 billion light-years in every direction. The universe itself is larger than this, significantly larger, possibly infinite. Everything beyond the horizon is real. Real matter, real galaxies, real structure, possibly real life and intelligence. But we will never observe any of it, ever. This is not a limitation of our technology. It is a fundamental feature of a universe with a finite age and accelerating expansion. And the acceleration matters enormously here. Dark energy, the cosmological constant, is causing the expansion to speed up. Galaxies that are currently close to the edge of our observable universe are being pushed toward the horizon by the accelerating expansion. In the long term, they will cross it. Their future light will never reach us. Our view of the universe will slowly contract. In the very far future, many tens of billions of years from now, all galaxies beyond the local group will have receded beyond our horizon. The Milky Way, Andromeda, and a few dozen gravitationally bound neighbors will be all that remains within our observable universe. The night sky will contain only the stars of our own galaxy, and perhaps the blended glow of the Andromeda merger, billions of years in the future. Everything else will be gone. Not destroyed, just hidden, permanently beyond reach. And the cosmic microwave background, the oldest light in the universe, our direct image of the universe at 380,000 years, will have been stretched by the expansion into wavelengths so long that they are undetectable by any instrument. The evidence of the Big Bang will have vanished from the observable universe. A civilization existing tens of billions of years from now, if one does, will have no evidence of the larger cosmic structure, no detectable cosmic microwave background, no visible distant galaxies, no observable early universe. They will be unable to determine that the universe had a beginning. They will be unable to discover that the cosmos extends beyond their galaxy. They will inhabit what looks, from their vantage point, like an eternal, static, isolated island of stars. The evidence that would tell them otherwise will have moved beyond their horizon. This is not poetry. This is straightforward physics. The accelerating expansion is erasing the cosmic record. In the very long term, the record will be gone. And we happen to live in the era when it is still here, still readable, still arriving at our instruments. This gives Webb's observations a character that goes beyond the usual scientific motivation. The early universe is not just interesting. It is disappearing, slowly, on cosmological timescales. But the direction is fixed, and the outcome is certain. Every image Webb takes of a galaxy from the first billion years is a document preserved from a universe that is actively erasing itself. Every spectrum, every photometric measurement, every confirmed redshift. These are records of something that will become permanently unobservable. not in our lifetime. Not in any lifetime we can currently imagine. But the direction is clear, and Webb is, in a real sense, racing against cosmic expansion to document the early universe before the evidence drifts further and further out of reach. This perspective is part of why the timing of Webb's launch, after nearly 3 decades of development, after years of delays, after a budget that swelled to $10 billion, matters beyond the usual calculus of scientific return on investment. We are at a particular moment in cosmic history. The universe is old enough to have produced complexity. Stars, galaxies, planets, chemistry, biology, intelligence, telescopes. All of this required time. The first 100 million years were dark. The first billion years were assembling. Complexity, as we recognize it, took several billion years to arrive. We are about 13.8 billion years into a universe that will last trillions of years. We are early. In one sense, we exist in the first 2% of cosmic time that will elapse before the last stars burn out. In another sense, we exist at precisely the point in that 2% when the early universe is most accessible. The cosmic microwave background is still bright enough to map in extraordinary detail. The early galaxies are still within our horizon. The oldest light in the universe is still arriving at our instruments. If we had arrived 50 billion years later, still early in cosmic time, by the standard of stellar evolution, we would have inherited a universe with none of this evidence. We got here when the evidence was still present. That is not something to take for granted. And Webb is the most powerful instrument yet deployed for reading that evidence while it is still there. The reionization of the universe is one of the topics where Webb is most sharply revising our understanding. After the cosmic dark ages, after the first stars ignited, those early stars and galaxies began producing ultraviolet photons, high-energy light, capable of ionizing hydrogen. Neutral hydrogen absorbs ultraviolet radiation very effectively. So, as the first sources of ionizing radiation switched on, they began carving out bubbles of ionized hydrogen in the surrounding neutral gas. These bubbles grew. They merged. Gradually, the neutral hydrogen that had filled the universe since recombination was converted back into an ionized plasma. This process, reionization, represents the second major phase transition in the thermal history of the universe. The first was recombination, when the plasma became neutral. Reionization reversed it. We know from observations of high redshift quasars that reionization completed by about 900 million years after the Big Bang. Quasars at very high redshifts show their ultraviolet light absorbed by neutral hydrogen in the intergalactic medium. Quasars at lower redshifts, seen when the universe was older, do not, because by then the intergalactic medium was fully ionized. The transition between these two behaviors in quasar spectra marks the end of reionization. But before Webb, the details of reionization were poorly constrained. When exactly did it begin? How quickly did the ionized bubbles grow? Which sources provided most of the ionizing photons? Rare, luminous quasars, or the far more numerous but individually faint galaxies? Was reionization spatially uniform or patchy? Webb is now providing data that addresses all of these questions. Its spectroscopic programs at high redshift are mapping the distribution of neutral hydrogen in the intergalactic medium across the reionization epoch with far greater detail than was previously. Persibler, a 2024 study using Webb near-spec spectra of multiple galaxies and quasars in the redshift range of 5 to 8, traced the evolution of the neutral hydrogen fraction through the latter stages of reionization with significantly improved precision. The results suggested that reionization was more extended in time than some simpler models had assumed, with substantial neutral hydrogen still present at redshifts corresponding to 800 million years after the Big Bang, and a relatively rapid completion between about 700 and 900 million years. This extended, patchy reionization is consistent with the broader picture that Webb is building of the early universe. It is not dominated by rare, spectacular sources. It is a complex tapestry of many galaxies in different environments, in different stages of assembly, producing ionizing photons at rates that vary enormously from object to object. Understanding reionization is not just about the thermal history of hydrogen. It is about which sources of light dominated the early universe. And knowing which sources dominated tells us about the nature of early galaxy formation. The evidence from Webb's reionization studies is pointing toward the faint, abundant, small galaxy population objects too faint to be individually detected by Webb in most observations, as the dominant source of reionizing photons, rather than the bright, massive galaxies that are more easily detected. This has implications for how we think about the role of the most spectacular early objects versus the more mundane, but far more numerous, smaller ones. The early universe was not lit primarily by brilliant beacons. It was illuminated by a vast multitude of small, dim candles, each one modest. All of them together, transformative. There is a piece of Webb's observational program that connects everything discussed above to a question that is more personal than any of them: whether the early universe produced conditions for life. This is a question that Webb was not primarily designed to answer. Its mission is to understand the formation of the first stars and galaxies, the growth of supermassive black holes, and the nature of the early cosmic web. But the implications of what it is finding touch on the conditions for life's existence. Life, as we know it, requires heavy elements: carbon, oxygen, nitrogen, phosphorus, sulfur, the elements of biochemistry. All of these are products of stellar nucleosynthesis. They did not exist until the first stars formed, fused hydrogen and helium into heavier elements, and then scattered those elements through supernova explosions. The more rapidly the first stars formed, the more rapidly they enriched the universe with heavy elements. The more efficiently the early universe recycled stellar material into subsequent generations of stars, the sooner the conditions for planets with complex chemistry could exist. If the early universe was more efficient than the pre-Webb models assumed, if it produced more stars, faster, if those stars enriched their surroundings more rapidly, then the prerequisite conditions for life could have appeared earlier in cosmic history than we previously thought. This does not mean life existed in the early universe. The conditions for life are necessary, but not sufficient. The right, heavy element abundance is just a starting requirement. You still need the right chemistry, the right planetary conditions, the right energy sources, and billions of years of biological evolution. Life as complex as anything we know is not going to arise in the first billion years. But the question of when the prerequisites for life first existed, when the universe had produced enough heavy elements in enough places to allow rocky planets and complex chemistry is pushed, earlier by Webb's finding that the early universe was more productive than expected. It is one of the less discussed implications of Webb's discoveries. But it sits there, quiet and significant. The universe that assembled faster than we predicted is also a universe that may have created the preconditions for life earlier than we predicted. What life might make of those conditions across 13 billion years of cosmic history is a question that no telescope can answer directly. But Webb has moved the starting line. As of early 2026, the James Webb Space Telescope has completed its first 3.5 years of science operations. It is functioning better than expected. Its mirrors are performing at or above specification. Its instruments are healthy. Its fuel situation is favorable enough that mission planners now project it could operate well beyond its 20-year design lifetime, possibly for 25 years or more. The observations completed in the first 3.5 years have already produced hundreds of peer-reviewed publications, papers on early, massive galaxies, papers on high redshift quasars and their host galaxies, papers on little red dots and their nature, papers on protoclusters and early large-scale structure, papers on early quenched galaxies, papers on the reionization history of the universe, papers on individual lens stars in the early universe, papers on the properties of the intergalactic medium at high redshift, papers revising the parameters of galaxy formation models to accommodate the new observations, papers proposing new theoretical mechanisms for early black hole seeding. The field has been moving fast, faster than it has in a long time. Webb data is publicly available within a year of observation for most programs, meaning that any astronomer anywhere in the world can download the raw data and analyze it. This has produced a distributed community effort on a scale that has not existed before. Independent checks of important results, rapid follow-up of interesting candidates, cross-validation using different analysis methods. The discoveries that have held up are the ones that have been checked this way. The problem of early massive galaxies survived because multiple independent teams with different pipelines found the same thing. The early quenched galaxy detections survived because spectroscopic follow-up confirmed them. The little red dots survived because they are clearly visible in every deep field imaging dataset, undeniable in their presence, even while their nature remains debated. The discoveries that were revised the most extreme early mass estimates. Some of the most distant galaxy claims were revised because the community found and understood the systematic errors. This is how science is supposed to work. And in the case of Webb's early universe results, it has worked well. The most robust conclusions from the first 3.5 years of Webb science are real discoveries. They are not going to go away as more data arrives. They will be better characterized, better understood, better contextualized. But the basic result that the early universe assembled itself more quickly and efficiently than the pre-Webb models predicted is established. What remains to be done is the harder work. Understanding why, not just identifying the discrepancy, not just proposing possible explanations, but actually determining which explanations are correct. This requires more data, more spectroscopy of early galaxy samples to build large enough statistical samples to test model predictions, more multi-wavelength follow-up of interesting individual objects, pairing Webb's infrared with X-ray observations from Chandra and XMM Newton, with radio observations from the Atacama Large Millimeter Array, with sub-millimeter observations from ground-based facilities. More theoretical work to build models that incorporate the revised astrophysics and make testable predictions for the next round of observations. More simulations, run with revised star formation and feedback prescriptions, to see whether the changes needed to match Webb's observations produce problems elsewhere, whether they overproduce stars at later epochs or underproduce the observed galaxy size distribution, or get the metallicity enrichment history wrong. Scientific models are constrained from many directions simultaneously. A proposed change to the initial mass function in the early universe can explain the early galaxy masses, but it also predicts specific things about the chemical evolution of those galaxies, about the ratio of different element abundances in early stars, about the energy input to the surrounding intergalactic medium. All of those predictions have to be checked against data. If the proposed changes work in one regime but fail in another, they are probably not right, or not the complete answer. The next few years of Webb observations will be crucial for this testing phase. The telescope is now in a mode of deeper, more targeted follow-up, programs specifically designed to test the new models. Observations at additional wavelengths to break degeneracies in the interpretation of early galaxy spectral energy distributions. Systematic surveys of gravitational lensing fields to probe the faint end of the early galaxy luminosity function, the many small galaxies that are individually too faint to detect in blank fields, but that may collectively contribute most of the stellar mass and ionizing radiation in the early universe. Observations of early galaxy clusters to track the assembly of the most massive structures and test predictions for protocluster formation rates. All of this is in progress. All of it is generating data. And all of it is being analyzed by a community of astronomers that is more prepared, more numerous, and more equipped with computational tools than at any previous moment in the history of observational cosmology. The picture of the early universe that emerges from all this work will be better than any picture we have had before. Not just more detailed, fundamentally more accurate, more honest about what actually happened in the first billion years, more precise about the physics that drove it, and Webb is the instrument that made it possible. There is a version of this story that emphasizes crisis. The models are wrong. The early universe is impossible. Everything we thought we knew is in question. This version is not accurate. The models need revision. The early universe is surprising. Some of what we thought we knew was incomplete. These are different statements, and the difference matters. Science is not a collection of eternal truths handed down complete. It is a process. A method for building the best available description of reality from the best available evidence, while acknowledging that better evidence will require better descriptions. The history of astronomy is a history of telescopes making the known unknown again. Galileo pointing a small tube at Jupiter and finding moons orbiting a planet that was not Earth, making the Aristotelian cosmology untenable. The 19th century discovery of stellar spectra revealing that stars were made of the same elements as Earth, making the boundary between terrestrial and celestial physics obsolete. Edwin Hubble identifying Cepheid variables in the Andromeda Nebula and establishing that it was a galaxy in its own right, millions of light-years away, making the Milky Way one island among billions rather than the whole universe. The discovery of cosmic acceleration through Type Ia supernova observations in the 1990s, making a static matter-dominated universe untenable and introducing dark energy. Each of these was a moment when better observations forced a better understanding. Each was initially uncomfortable. Each turned out to be progress. Webb's early universe discoveries are in this tradition. Not as dramatic as establishing that the Milky Way is not the whole universe, but meaningful. A genuine revision of what we know about how the first chapter of cosmic history was written. The early universe assembled itself faster, more efficiently, and into more organized structures than the pre-Webb models captured. That is a real finding. It requires real revisions. And the revisions, when they are complete, will give us a better picture of where everything came from, including us. We exist at a specific moment in cosmic history, 13.8 billion years after the beginning. Late enough that stars have had time to forge heavy elements. Late enough that planets have had time to form and cool and become habitable. Late enough that biological evolution has had time to produce intelligence and curiosity and the desire to understand origins. But early enough, and this is the part that is easy to miss, that the origins are still visible. The cosmic microwave background still fills the sky. The early galaxies are still within our horizon. The most ancient light in the universe is still arriving at Earth, still carrying information about the universe's dawn that can be read by instruments sensitive enough to detect it. Webb is that instrument, the most powerful yet built for this purpose. And the fact that we built it precisely when we did, when the cosmological model was mature enough to make precise predictions, when our technology was capable of building the required instrument, and before the expansion of the universe has moved, the most ancient objects out of reach, is either a remarkable coincidence or a reflection of the fact that intelligence in this universe had to arise. At roughly this point in cosmic history, to have access to this evidence. Whatever the reason, we are here. The instruments that made Webb possible are worth understanding on their own terms. Not as a list of technical specifications, but as an explanation of why Webb can see things that nothing before it could. The primary mirror is the obvious starting point. 21 feet and 4 inches across. That number sounds large, but the significance is not just the size. It is the collecting area. The amount of light a telescope gathers is proportional to the area of its mirror. Webb's mirror has roughly 6 times the collecting area of Hubble's primary mirror. This means that for a source of a given brightness, Webb collects photons 6 times faster than Hubble could. For the faintest early galaxies, sources so dim that even long Hubble exposures collected only a handful of photons. The difference between 6 photons and 1 photon is the difference between detecting something and seeing nothing. But collecting area alone does not explain Webb's transformative power. What matters equally is wavelength. Hubble observes primarily invisible and ultraviolet light. Webb observes primarily in the near-infrared and mid-infrared, at wavelengths between roughly 0.6 and 28 microns. This wavelength range is where the most distant objects in the universe, those with the highest redshifts, the farthest back in time, emit the bulk of their observable light. A galaxy that emitted its intrinsic ultraviolet and visible light 13 billion years ago has had that light stretched by the expansion of the universe into the near-infrared by the time it arrives at Earth. For Hubble, that light is in the infrared, where Hubble's detectors have limited sensitivity. For Webb, it is right in the sweet spot. This is why Webb can observe galaxies at redshifts above 10 in detail that Hubble could barely hint at. It is not that Webb has fundamentally different physics. It is that Webb is tuned to exactly the wavelengths where the early universe's light arrives after 13 billion years of cosmic stretching. The 4 instruments aboard Webb each contribute differently. NIRCam, the near-infrared camera, is the primary imaging instrument. It uses 2 modules, each containing a short wavelength channel and a long wavelength channel, allowing it to simultaneously image at multiple near-infrared wavelengths. This simultaneous multi-wavelength imaging is what enables the photometric redshift technique. By measuring a galaxy's brightness at many wavelengths at once, astronomers can estimate its redshift from the pattern of its colors without spending time on a spectrum. For building large statistical samples of early galaxy candidates quickly, NIRCam is invaluable. NIRSpec, the near-infrared spectrograph, is the instrument that provides definitive answers. It can simultaneously take spectra of up to about 200 objects at once, using a system of tiny configurable shutters called a micro-shutter assembly that can be opened and closed individually to select specific targets across the field of view. This multi-object spectroscopy capability is what has allowed surveys like JADE's to obtain thousands of galaxy spectra in reasonable amounts of telescope time. Before NIRSpec, confirming a single high-redshift galaxy spectroscopically required dedicating an entire observation to that one object. NIRSpec can confirm 200 in the same time. This is the capability that transformed Webb from a capable imaging telescope into a statistical engine for the early universe. MIRI, the mid-infrared instrument, operates at longer wavelengths, between 5 and 28 microns. This range is sensitive to thermal emission from dust, to molecular spectral features in the mid-infrared, and to the most extremely redshifted sources. MIRI has been used to study the properties of early galaxy dust and star formation in ways that complement the shorter wavelength NIRCam and NIRSpec data. The fourth instrument, the fine guidance sensor with NIRIS. The near-infrared imager and slitless spectrograph serves double duty as a guidance sensor for precise pointing and as a science instrument capable of slitless spectroscopy. This slitless mode is particularly useful for identifying emission line galaxies. Galaxies producing strong spectral lines from ionized gas across wide fields without needing to pre-select targets. Together, these four instruments provide a suite of observational capabilities that is qualitatively different from anything that preceded Webb. Not just more sensitive, more versatile, more capable of asking the specific questions that the early universe poses. The way observational cosmology has been done before Webb also deserves a moment. Because part of what makes Webb's impact legible is understanding the limits of what came before. For most of the 20th century, studying the early universe was largely impossible. The universe, at redshifts above 3, when it was less than 2 billion years old, was essentially terra incognita. A handful of bright quasars had been identified at high redshifts by the 1980s. They were too bright to be normal galaxies. They were the blazing beacons of accreting supermassive black holes in the centers of distant galaxies, their light outshining their host galaxy by factors of hundreds or thousands. Normal galaxies at those redshifts, the ancestors of today's galaxies, were too faint to detect with the telescopes and detectors of that era. The Hubble Space Telescope, launched in 1990 and repaired in 1993, changed this dramatically. The Hubble Deep Field, in December 1995, was a turning point. A 100-hour exposure of a tiny patch of sky in the constellation Ursa Major revealed thousands of galaxies, most of them distant. Some of them at redshifts of several, corresponding to when the universe was only a few billion years old. The Hubble Deep Field showed that the early universe was populated by galaxies. It gave astronomers the first real census of the galaxy population as a function of cosmic epoch. Over the following 2 decades, Deeper Hubble surveys the Hubble Ultra Deep Field. The extreme deep field pushed this census further back in time. By the time Webb launched, Hubble had identified galaxy candidates at redshifts above 10, had confirmed galaxies spectroscopically at redshifts up to about 11.1, and had provided the statistical foundation on which the standard model of galaxy formation was calibrated. The ground-based facilities also contributed enormously. The Keck telescope in Hawaii, the Very Large Telescope in Chile, the Subaru telescope in Hawaii, all of them equipped with spectrographs capable of confirming galaxy redshifts and measuring physical properties. The Atacama Large Millimeter Array, a network of radio antennas in the Atacama Desert that observes at millimeter and sub-millimeter wavelengths, came online in the early 2010s and added the ability to detect cold, gas, and dust in early galaxies, tracing star formation and molecular gas content at high redshifts. X-ray satellites. Chandra and XMM Newton detected high redshift quasars and X-ray bright active galactic nuclei, probing the accretion history of early black holes. All of these instruments had reached the limits of what they could do without a new generation of capability. They had answered the questions they could answer and exposed the questions they could not. Webb answered some of those exposed questions and created new ones. The specific numbers that have come out of Webb's early universe surveys are worth dwelling on, not just as data points, but as a way of making concrete what might otherwise remain abstract. The JADE survey, as of early 2026, has spectroscopically confirmed galaxies at redshifts ranging from about 3 to 13 and beyond. At redshifts above 8, when the universe was less than 650 million years old, JADES has confirmed dozens of galaxies. At redshifts above 10, when the universe was less than 500 million years old, confirmed spectroscopic samples now number in the dozens from multiple surveys combined. At redshifts above 12, when the universe was less than 370 million years old, a handful of objects have now been spectroscopically confirmed. The galaxy JADES GSZ 14-0, confirmed in early 2024, established a then-record redshift of 14.32. That corresponds to a look-back time of 13.5 billion years. The universe was approximately 290 million years old when the light we observe from this galaxy was emitted. It has been traveling toward us for 13.5 billion years. The galaxy itself, at that epoch, had a stellar mass estimated at a few hundred million solar masses, modest compared to the Milky Way, but already surprisingly substantial for an object so early. It showed evidence of oxygen emission in its spectrum, indicating that stars had already formed and gone through their entire life cycles, creating and distributing heavy elements well before the epoch of observation. Oxygen in a galaxy 290 million years after the Big Bang. Heavy elements produced by the first generation of stars, scattered by their supernova deaths, incorporated into the gas that formed subsequent stars, and already measurable in the spectrum of a galaxy that was forming when the universe was barely 2% of its current age. This is not just a record. It is a demonstration of how fast the early universe was working. Star formation efficient enough to produce and distribute heavy elements within the first few 100 million years. The universe did not ease into complexity. It arrived there at a sprint. The gravitational lensing programs that Webb has pursued alongside its blank field surveys have added another dimension to this picture. Gravitational lensing, the bending of light by massive foreground objects, magnifies distant background sources, making them appear brighter and larger than they would otherwise. Webb has targeted numerous massive galaxy clusters specifically to exploit their gravitational lensing power. These clusters act as natural cosmic telescopes. They gather and concentrate light from sources behind them, stretching and brightening those sources in ways that allow Webb to detect galaxies and even individual stars that would be invisible in blank fields. The Pandora's Box observations, released in January 2023, combined Webb imaging of 4 galaxy clusters and their surrounding fields. The result was an image containing thousands of galaxies across a wide range of redshifts, including highly magnified sources that could be studied in detail, not otherwise possible. Among the most scientifically valuable results from gravitational lensing programs has been the ability to study the internal structure of early galaxies. In blank fields, even Webb's resolution is not enough to resolve the internal morphology of the most distant galaxies. They appear as unresolved or barely resolved points of light. But through a gravitational lens, the magnification can stretch an early galaxy across many pixels of Webb's detectors, revealing its internal structure. Some early galaxies observed this way show compact, clumpy, star-forming regions, dense knots of star formation embedded in more diffuse galaxy envelopes. This clumpy morphology is different from the smooth spiral structure of present-day galaxies like the Milky Way, and it is consistent with theoretical models of early galaxy formation in which gas was denser, more turbulent, and more prone to fragmentation into massive star-forming clumps. Others show more uniform, compact light distributions, consistent with the compact, massive galaxies, often called red nuggets, that are inferred to be the precursors of today's massive elliptical galaxies. And some show disturbed, asymmetric morphologies consistent with ongoing mergers between small galaxies. The bottom-up assembly process that the hierarchical cold dark matter model predicts. The diversity of early galaxy morphologies revealed through gravitational lensing is itself informative. It tells us that even at the same cosmic epoch, early galaxies were not a uniform population. They had already differentiated into different types, different structures, different histories. The early universe was not a simple or uniform place. It was already complex, already varied, already generating the diversity of object types that we see reflected and amplified in the present-day galaxy population. There is something else that comes through clearly from Webb's first years of operation that is harder to quantify than galaxy masses or black hole masses, but that might be the most important thing Webb is establishing. The early universe was a violent place. Not violent in a sense that requires metaphor, violent in the physical sense. Gas moving at thousands of miles per second, star formation rates hundreds of times higher than anything happening in the Milky Way today, supernovae detonating at rates that would be incomprehensible by today's standards, active galactic nuclei blazing with luminosities thousands of times greater than the entire present-day Milky Way, gas being blown out of galaxies, heated to millions of degrees, scattered into the surrounding intergalactic medium, dark matter halos merging with each other at rates that have since declined by orders of magnitude. This violence is not incidental. It is the mechanism. The early universe assembled its complexity through extremes, through conditions that do not exist in the present-day universe except in the most active environments, galaxy cluster mergers, quasar outflows, starburst-driven winds. Those extreme processes, now rare, were once universal. They shaped the initial conditions for everything that followed. Every galaxy today, including the Milky Way, including the modest spiral galaxy that eventually produced a solar system with a habitable planet, is in some sense a product of those early violent episodes. The heavy elements in every human body were made in those early, intense, star-forming environments. The dark matter halos that organized the matter into structures were assembled in those early merger-dominated epochs. The supermassive black holes at the centers of galaxies were seeded and grown in those early extreme conditions. We are the downstream consequence of a universe that began not gently, but furiously. Webb is documenting that fury, quantifying it, constraining the physics that produced it. And what the data is showing is that it was even more extreme, even more productive, even more organized, even more fast-moving than the models written before Webb could tell us. The early universe was not assembling itself on the timescales the equations predicted. It was ahead of schedule, by amounts that forced the people who wrote those equations to go back and look for what they had missed. That process of looking and finding and revising and looking again, that is what Webb is enabling. And it is not finished. Looking ahead from early 2026, the immediate priorities in early universe research, informed by Webb, include several specific programs that are either underway or scheduled. The Ultra-Depth Near-Spec Survey Program, a planned multi-cycle observing program using near-spec to obtain extremely deep spectroscopy across several carefully selected fields, will push the program spectroscopic sample of high redshift galaxies to much fainter magnitudes than the current samples. This is important because the existing spectroscopic samples are biased toward the brightest objects at each redshift. The faint end, the numerous but individually dim small galaxies that may constitute the majority of the early galaxy population, and that may be responsible for the bulk of reionization, is poorly sampled. The ultra-deep spectroscopic programs will begin to address this. The Treasury programs, targeting massive galaxy clusters for gravitational lensing, will continue to identify individual, highly magnified early galaxies and early stellar objects, building the sample of objects that can be studied in physical detail rather than just statistically. Multi-wavelength follow-up campaigns pairing Webb detections with observations from Chandra, from the Atacama Large Millimeter Array, from the Very Large Telescope, and from ground-based optical facilities will add wavelength coverage and deepen the physical characterization of key objects, particularly the little red dots, whose nature remains unclear. And Webb will continue its wide-area survey programs designed to cover more sky area at the expense of sensitivity, finding the rare, extreme objects that deep but narrow surveys miss. The tension between depth and breadth, between sensitivity to faint objects in a small area and detection of rare objects across a larger area, is a fundamental feature of observational cosmology. Webb is pursuing both. And the combination is producing a picture of the early universe that is more complete, more statistically robust, and more physically detailed than anything that existed before December 25th, 2021. What Webb has established in its first years of operation is not a single discovery. It is a shift in the empirical foundation of a field. Before Webb, our knowledge of the galaxy population at redshifts above 8 was built on a few dozen photometrically selected candidates with a handful of spectroscopic confirmations. The statistics were too sparse to make definitive statements about the early galaxy mass function. The models were calibrated on far better data at lower redshifts and extrapolated with reasonable assumptions to these early epochs. Those assumptions turned out to be wrong, not catastrophically, not in ways that require rebuilding cosmology from scratch, but in ways that required revising the astrophysics embedded in the galaxy formation models. The revisions are still being worked out. The models are being updated. The predictions for the next round of observations are being written. And when Webb tests those predictions, which it will, in the years ahead, the field will learn whether the revisions were right, or whether there is another layer of unexpected behavior waiting to be discovered. That is the nature of this enterprise. It does not converge to a final answer. It converges toward better and better approximations of the truth. Each round of observations narrowing the uncertainty. Each revision of the models incorporating more of what is actually there. Each new discovery pushing the boundary of what we know and what we do not. Webb pushed that boundary by an enormous distance. It will push it further still. And when the next generation of telescopes arrives, the extremely large telescope on Cerro Armazones in Chile, with its primary mirror spanning about 128 feet, capable of taking spectra of early galaxies with 100 times more light gathering than any existing ground-based telescope, or the Nancy Grace Roman Space Telescope, designed to survey the sky in the infrared across an area hundreds of times larger than Webb's typical field of view. The foundation that Webb has laid will be what they build on. The early universe that Webb has begun to document will be documented in far greater detail. The models that Webb has forced into revision will be tested against far larger and more precise datasets. The questions that Webb has sharpened will either be answered or replaced by better questions. This is the forward direction of science. Not a straight line, not a clean progression, but always moving toward a more accurate, more complete, more honest description of what is actually out there. What is actually out there, it turns out, assembled itself faster than we thought. That is the finding, and its implications will be worked through for years. The relationship between Webb's observations and the theoretical models they are challenging is worth one more examination, because there is a human dimension to this that gets lost when we talk only about galaxies and redshifts and stellar masses. The people who built the standard model of galaxy formation, who wrote the simulations, who calibrated the feedback prescriptions, who predicted the early galaxy mass function, spent decades of their careers on that work. These are not simple calculations. The major cosmological simulations programs, like Illustris TNG, Eagle, Fire, and Simba, took years to develop, cost millions of dollars in supercomputing time, and involved teams of dozens of researchers refining their implementations of star formation, physics, feedback, and chemical enrichment. These simulations are genuine scientific achievements. They explain things that could not previously be explained. They made predictions that were confirmed by observations. They represented the best understanding the field had of how galaxies form and evolve. And then Webb found that their predictions for the early universe were off. The response from the simulation community has been exactly what you would hope for from a mature scientific community. Not denial, not resistance. Immediate, serious engagement. Within months of the first Webb early galaxy results being published, papers appeared from the major simulation groups, analyzing why their models underpredicted the early massive galaxy population and what changes to the models could improve the agreement. Some papers explored whether changes to the feedback implementation could account for the discrepancy. Others looked at whether the stellar initial mass function needed to be modified. Others examined whether the assumed relationship between star formation rate and gas density was appropriate for the extreme environments of the early universe. All of this happened in the open literature, in published papers available to anyone. debated at conferences and in journal peer review, improved by the back and forth of scientific argument. This is not science in crisis. This is science working. The difference is important. A crisis is when you find that your foundational assumptions are wrong. When the data contradicts not just the details, but the core architecture of your theory. What Webb found is not that. The core architecture, the Big Bang, inflation, cold dark matter, dark energy, was not contradicted. The astrophysical submodels built on top of that architecture were shown to be incomplete. And in a field as complex as galaxy formation, finding that your astrophysical submodels are incomplete is not a crisis. It is the normal condition. Galaxy formation is genuinely hard. The physics spans more than 20 orders of magnitude in spatial scale, from the subatomic processes of nuclear fusion in stellar cores to the megaparsecond scale flows of gas in the cosmic web. Simulating all of it from first principles is not possible. Approximations are necessary. The approximations used before Webb were the best available calibrated against the data available. Webb provided better data. The approximations need to be improved. That work is underway. There is one more aspect of Webb's early universe program that connects to something very old in the human experience of the cosmos. The desire to see the beginning, not to understand it abstractly, not to describe it in equations, but to actually look at it, to collect light that left the universe's first structures and have it arrive at a mirror and form an image. This desire is not unique to scientists. It is something more fundamental. The impulse to look back, to trace the chain of cause and effect as far as it goes, to find, if possible, the moment when everything started. Humans have been doing this as long as we have been able to build telescopes. Every increase in telescope aperture has been, in part, a reaching further back into cosmic history. Because looking farther away means looking further back in time. The stars we see tonight are not where they are now. They are where they were when the light, now arriving at our eyes, departed. For nearby stars, the delay is years to centuries. For the galaxies in Andromeda, 2.5 million years. For the most distant galaxies Hubble could see, billions of years. For the galaxy's Webb is now observing at redshifts above 12, more than 13 billion years. When Webb takes an image of a galaxy at redshift 14, as it has now done, it is collecting light that left that galaxy when the universe was less than 300 million years old. That light has been traveling through space for longer than the solar system has existed. It was launched before any of the stars in our galaxy were born. It crossed the expanding universe for 13.5 billion years. And then it landed on a gold-coated mirror, was focused by optical elements cooled to within a few dozen degrees of absolute zero, roughly minus 390 degrees Fahrenheit, or about minus 235 degrees Celsius, and was converted into an electronic signal by infrared detectors, analyzed by computers, and turned into a number on a plot of galaxy properties versus redshift. And, from that number, scientists are reconstructing something about what the universe looked like when it was taking its first steps. That is extraordinary, that this is possible at all. That the universe is old enough and transparent enough that we can look back this far. That we have built the instruments to do it. That there are people alive right now who spend their days analyzing these ancient signals and arguing about what they mean. and that what they have found is that the universe at its dawn was more active, more organized, more efficient, and in some ways more strange than the equations predicted. We have been reaching for the beginning. For as long as we have known, there was one to reach for. Webb has reached farther than anything before it. And what it has found has made the beginning stranger and more remarkable than it already was. There is something worth saying about the pace at which Webb's results have moved the field. In normal circumstances, major revisions to well-established models take years. A single observational result, however striking, takes time to be accepted. Other groups need to reproduce it. Systematic errors need to be ruled out. Theoretical explanations need to be developed and tested. The revision needs to be incorporated into simulations. New predictions need to be made and tested. The whole cycle, from initial anomalous finding to revised and accepted model, typically takes 5 to 10 years in a mature field. With Webb, the cycle has been compressed, partly because the observations were so clear. The excess of early massive galaxies was not a marginal signal, visible only in certain analyses. It was large enough that independent groups with independent data and independent pipelines found it simultaneously, partly because the community was prepared. Theorists had thought about the early galaxy problem for years, using Hubble data. When Webb data arrived, the theoretical frameworks needed to interpret it were already in place. And partly because of the culture of rapid, open science that Webb has encouraged. Data releases within months of observation. Results posted as preprints before peer review. Open code repositories where analysis pipelines can be inspected and reproduced. This openness has compressed the timeline of the scientific process. Not by skipping steps, the peer review, the independent reproduction, the systematic checks still happen, but by allowing them to happen in parallel rather than in sequence. Multiple groups checking the same results simultaneously rather than waiting for one group to finish before another begins. The result is that the field's understanding of the early universe has advanced in 3.5 years by an amount that might previously have taken a decade or more. That is not primarily a function of Webb being more powerful than previous telescopes, though it is. It is a function of a community that was ready to move fast when good data arrived. And the data that arrived was better than expected. Webb's performance has exceeded its design specifications in several areas. Its sensitivity is higher than the pre-launch estimates predicted. Its photometric calibration has been achieved at higher precision than was expected early in the mission. Its pointing stability and thermal stability have been excellent. The result is that the science programs that were designed for a telescope meeting its specifications have, in many cases, achieved their scientific goals faster than planned. Survey programs designed to take multiple years have accumulated data ahead of schedule. Deep spectroscopic exposures are achieving the required signal-to-noise in shorter time than anticipated. This means that the scientific return on Webb's mission will likely be higher than originally projected. More science in the allotted mission lifetime. More constraints on the early universe. More tests of the revised models that the first 3 years of data have forced. For the people who spent decades advocating for Webb, designing it, building it, testing it, and watching it finally launch after years of delays, there is something satisfying in this. Not just that it works, but that it works so well. That the instrument they built is doing more than it was asked to do. The James Webb Space Telescope looked at the dawn of the universe and found what scientists were afraid of. Not that the fundamental framework was broken, not that the Big Bang was wrong, or that cold dark matter was a fiction, or that general relativity had failed in some new regime. But that reality, in its earliest chapter, was working faster and harder than our best models had captured. The early universe assembled its complexity ahead of schedule, by amounts that matter, by amounts that forced the revision of the astrophysical models built into decades of careful simulations. The models will be updated, are being updated. The simulations are being rerun with new prescriptions. New predictions are being made, and Webb will test them and find the next layer of what we got right and what still needs to be fixed. That is the project. That is what science is when it is working correctly. And somewhere in the ancient light, arriving at Webb's mirror right now, photons that departed galaxies when the universe was young and dense and furiously productive, photons that have been traveling through expanding space for more than 13 billion years, is the next finding, the next confirmation, the next surprise, waiting to be read by an instrument finally good enough to read it. Good night. The early universe assembled itself faster than we predicted, and we are still learning, in precise and quantitative detail, exactly how fast and why, and what that means for the story of everything that came after, including us.